Good evening, everyone. Welcome to week 9 live interactive session of Advanced Computer Network course. This week's topic of discussion was data center networks. So let's slowly get started with what DCN is. What are the different types of DCN, the components that are present in a DCN, and DC, I mean, basically data center, and then we will slowly move to the different kind of applications that the big giants run in the data center, and then we'll see in what way the normal networking is different from a data center networking. Okay. Yeah, so we'll get started with data center. So what is a data center? Yeah, one by one, we'll get started. Am I audible? Can somebody please confirm? Hi, good evening. Am I audible? Yeah, thanks. Yeah. So, what is a data center? As the name says, it's a center where there is a lot of data. Right. A DC is actually a facility which comprise of, in simple terms, we can say DC is a facility which comprise of compute, storage, and network. Okay. So this houses various computer systems, associated components, storage, um, computer system components. When we have you ever observed, like when you use your laptop or your desktop for a long duration of time, and sometimes when the power is on, the desktop or the laptop heats up. Especially my laptop, it just heats up if I use it for maybe 8 to 9 hours continuously. Sometimes forget to shut it down also, and the heating becomes very severe, right? So with a simple 16 core laptop, and I'm seeing the heating issue. We can actually feel it if you touch and see your PC or your laptop. You can actually feel the heat generated, right? So in a data center facility, when there are they actually host lakhs and lakhs, I mean, uh, thousands of servers. When all these, in addition to servers, they host computer system components. So they will have servers, there will be a lot of network devices, like how we have seen, right? What are the middle boxes, the routers, the switches, the all the available middle boxes, all of them will be hosted there. And when we power on all of them together, a lot of heat gets generated, and thus a dedicated cooling system is needed. Then we need, of course, power, and then power backup is needed. So a data center, so basically it's a facility which is used to house computer systems and associated components such as networking, storage system, cooling, and uninterrupted power supply, etc., etc., etc. So typically they host a large number of heterogeneous computer systems. So it doesn't matter that all the systems has to be uniform. So the systems or the servers that are kept in the data center are normally heterogeneous in nature. By heterogeneous, it means that one server could be from Dell, one could be from HP, another could be from Lenovo, another could be from another vendor, XYZ. Same way, switches also could be, one could be from Cisco, Juniper, Arista, or any XYZ person. So these are heterogeneous systems and devices are normally kept in the data center. And it could be so a data center could be as small as a small room, or as big as a house house, or as big as a building, or it could be as large as a stadium, like spread across acres of land. So that's what typically a data center. Basically, it comprises of a lot of computer systems, storage devices, compute systems, networking devices, and the necessary powering and cooling needed for these systems to be up and running. So maybe I can show you like, so this is how a typical screen visible. Yeah, yeah, it's visible, right? Yeah. So if you see here, this is I just googled Google data center, and these are the pics that came up in my iPad. So if you can see people working on somebody, this is how when all the servers are working, they're blinking. You can see the lightings, the connections are done. When you connect, all these cabling is done. The ports will be blinking, right? They will detect the status, it's operationally up, and it will be blinking. So this is how the mm, data center looks like. And if you can see, yeah. So there is another picture. Yeah, which I wanted to show. Right, yeah. So when you want to actually make a, you can see how tall is this, right? So these are, if you can see, the vertical lines are there, right? These are actually the racks over which the servers and the switches and all the devices are mounted on, okay? And see, when an operator or somebody wants to look into a connection, say if so somebody have climbed on top of a ladder and then looking onto it, right? So this is available in the Google. So this is the whole cooling system, how they are ensuring the AC and the temperature inside the data center. That is this. Also check it online. Okay. This is like somebody monitoring the network. So in a different place, the DC, in the DC, they have a lot of devices interconnected, right? So one need to monitor also. If something goes wrong, one should be able to figure it out. So these giants do have a full-fledged monitoring system in place, and operators will be monitoring the system also, checking at the dashboard and other using other mechanisms. So these are people working on the DZ. Okay. Yeah, I just showing it through. That's it. Right. So that is how typically the DZ looks like. Okay. Mm. Now, so as I said, there will be a lot of cabling, powering, ventilations, etc., etc., will be needed. And when all these uh, like all the racks are completely filled with servers, the amount of heat they generated will be very high, and it's very important that proper refrigeration or cooling is taken care so that the devices work as expected. So that is something, yeah. Then now let's take a look at what are the different types of data centers. Okay. Typically, this lecture is like theory. There is no problems as such to solve here. So we have some MCQs which I'll look into it towards the ones we just quickly skim through all the topics that professor covered in week 9. Then we'll go to the MCQ questions. Okay. Types of data centers are typically we have enterprise data centers. Enterprise data centers are typically constructed for their own consumption. Like the company will have, for example, let's take the example of maybe uh, Indian Oil Corporation or HPCL or any maybe banks or any example. These enterprises actually deals with a lot of data, right? Uh, the gas booking mechanism, petrol billing, and those things. We go and fill the petrol from the vendor, but these companies would be distributing to the pump owners, and so they will have their own itinerary management and many things. Or let's take the example of a bank itself. There are a lot of banking transactions that happens, right? So there are lakhs of people or millions of people having account in the bank. All these details are stored in databases, which are actually in the data center of these banks. So those will be the enterprise data center. They own it. They have their own data center. It's custom built to meet their requirement of the organization. They will only be handling these data centers. So enterprise DC is constructed and owned by companies for their and they will have the whatever are the requirement for the kind of application that they are running in the DC. Accordingly, it will be custom built for meeting their requirement. So that those are enterprise data centers. The another type of data center is specialized data centers, such as the one that Facebook have. So Facebook runs, it's a social networking application, right? So Facebook has this data center where anybody who is having a Facebook account, all the details of all these people are there in their data center, stored in their server and databases. Okay, so that is a specialized data center for built for big applications. For big applications, specialized DCs are built by the company. For example, Facebook. Then we have Bing, Google search, web search applications. For web search applications such as Google, Bing, etc. So these are specialized data centers built for this one big application. Another set is um, cloud data centers. In cloud data center, which is an example of a cloud data center? Amazon EC2, uh, Windows Azure, Microsoft Azure. So here, cloud data center, here they provide the necessary infrastructure, and people host their data in these data centers. So it's not like you have the in-house data center. Like I've told, enterprise data center, those enterprises have the hardware in their data center. They own it. Whereas in cloud data center, Microsoft or Amazon will have the servers kept in their data center, and that will be used by, consumed by people for deploying their application and all that. Okay, so that's the example of cloud data centers. So, like as we saw, these data centers actually can, as I told, it can be as small as a room in a house, or as big as a flat, or as big as a playground or a stadium, or even triple or double the size of that. So the ones that Google or Amazon owns and all is like bigger than the size of a stadium, etc. I think sir have given some analogy, right? The biggest stadium in India, I think the one that Microsoft owns, the DC that Microsoft owns, is like double or triple the size of that cricket stadium that is in Gujarat. I think the largest one in India. So it could be as large as that as well. So the number of servers that these data centers host varies from as high as 10 to 1,000 K servers with very high power consumption, and very costly high power consumption. Because to set up such a data center, it's lot of infrastructure. Money goes into building the infrastructure and power, etc. A lot of money, and there is a lot of power consumed. There are a lot of servers. Typically, they are actually really big. So we actually use these servers on a day-to-day basis, right? Like when we are just even Googling around. I think I showed you the Google data center. That's what I Googled. Okay. That actually I would have got it from the Google's data center only, from the search engine, the app application that they have hosted in their data center. In India also, yeah, we do have a lot of companies now host their data centers. I think in Hyderabad we have, I think, couple of companies hosting their data center. Bangalore, Bombay, Delhi, various cities we have. And also there is a government of India, the National Data Center, where a lot of government companies and organizations host their data. There is this national data center that have come up, and it is there in Delhi, Pune, Hyderabad, Chandigarh, etc. There also a lot of our like digital, as part of the Digital India campaign, the e-office, e-tags, a lot of those things run in the national data center in India. All right. So that this was based on the this is one classification type of DC, who owns it, where, and all that. And another classification of data center is based on the uh, size and power usage. So basically, another DC classification based on the size and power usage. In case if there is any, if the screen is not visible, or if the audio is visible, just unmute yourself and let me know, okay? Right. Yeah. Okay, thanks. Yeah. So, so based on the size, how we classify the data center is like macro data centers. The other one is micro data centers. Then we have nano data centers, and we also have container data centers. So as the name suggests, macro is the large ones that we were just talking about, the ones that Google, Amazon, Microsoft, Facebook, and other giants have to be massive in size, like lakhs of servers, lakhs of more servers, very massive ones, lakhs of servers, and high power consumption, etc. And the applications that demand large computational and storage capacity and all will be hosted in these data centers. Okay. The other one, micro data center is a comparatively smaller one, which will be having maybe thousands of servers or so. Would be in a more smaller area. Energy consumption also will be smaller, and these data centers would be built more closer to urban areas. In general, telcos normally go for such micro data centers, and the telecom providers are the one who normally goes for such. Could you please mute? Excuse me, could you please mute yourself? Right, thanks. Hmm. So, yeah, so micro data centers are generally used by the telco people, wherein, I mean, the operators, the 4G, 5G mobile operators, right? You can see how, I mean, how much of, how many people use and the amount of data exchange that happens. So, they also run a lot of their, especially in with 4G and 5G, a lot of uh, management applications run in the cloud, and to be nearer to the exchange points. Micro data centers are normally used by telco operators, and they are built more close to the urban areas. So, which will be smaller in size with comparatively lesser energy consumption, as they will be hosting only lesser number of servers there. The other one is the container data center. So container data centers are even smaller. So we know, right? In normally, how does a container look like? The ones that we use for shipping and things, like there will be a large box, right? And inside that, they actually build up inside the container. A data center is built. So it will have the racks, cooling system, networking done, all that is necessary for so it will be a more like a more miniature DC, which is built inside a container. So a mini DC built inside a container is that is a container network. The advantage of such container data centers are their speed of deployment. It's very fast. It is mobile. You can move it from one place to another, and smaller operational cost, etc. And the another set of DC is the nano DC. Nano DC is something which is even smaller than the container data center, and is no, nano data center or NADA. This is more like a very very smaller one that is perceived to be near to the end user facility, such as our Wi-Fi router, etc. So this is not a typical classical use of a data center, as we know. And the the purpose also I'm not very clear, but yeah, this is another another classification of a data center here, type of data centers here. So as we have seen, typically, I mean, as I have been telling, what does DC contains compute, servers, storage and network, servers or compute, storage and network. Yeah. Yeah. So, what are these servers? So, what is a server? Anybody? What is a server? So, like any application that we are currently sitting here and using, like even the Google Meet application that we are consuming, it's actually a service a service that we are actually consuming, right? The when I am using it, I am the client, and Google, who is providing me the Gmeet application, is the server, right? So, servers are nothing but computers that provide us the services. I think in the undergrad and all, we start with this terminology of client server communication, right? So, we take the example of a simple example of a chat server where we will have two devices. One will be the client, one will be the server, and then we write our initial simple chat application program wherein the client will send a hi, server will respond back with a hello, right? So this is a simple chat application, but in general, server is a nothing but it's a computer that provides a specific service to us. Okay, so I mean, there are many online services that we are consuming, right? Any example? Can somebody cite an example of a service? You can put it in the chat. Okay. Okay, so these applications or the services that people consume, these are typically designed for serving large number of requests, and they run in what is known as physical servers, right? Large devices with lot of compute power. Some of them will have they are large servers with lot of compute. Some will have lot of cores. Some will have GPUs. Based on the purpose the server is being used, accordingly the capability of the server also would vary. Okay, so it's a hardware like our laptop or our desktop machine. It's also a hardware device. Okay, so in general, in data centers, how it looks like is we will have what is known as racks. So rack will be like this. Okay, and we will have rails here. So I don't know how to draw a 3D diagram of it. Okay, so we will have rails like this. And these servers that we normally keep in the data center are like this flat box. It is not the vertical desktop. It will be like our laptop, but little more thicker and larger. Okay, so these servers, okay, these are normally put into inside. So this will have a depth. This has a depth. Okay, it has a depth. This is a rack, and the server that I'm telling you, this will be inserted here. This will be one server. Another server will be inserted like this. The servers are actually stacked one on top of the other in the rack. And these servers, which I told you here, these like it can be based on the thickness of the server. We call them like okay, this is a cube. Sorry, it will look like okay. Mm, yeah, I'll just yeah. So based on the thickness of these servers, like how thick it is. Thickness will be here. Like how thick the server is, we classify them as 1U server, 2U server, 4U server, etc. Okay. So basically, based on the thickness, if it is a typical data center rack can hold, I think, up to 40 1U servers and 40 or 42. And if we are putting in 2U servers, then it will be 20. If we are putting 4U servers, the number of servers that we can stack in a rack would come down accordingly. It's not that all the servers has to be of the same thickness. We can mix up and put it across. Maybe I'll show you. Okay, let me share the screen. I will show. Yeah, can you see this? You can see this picture, right? Yeah, so this is a rack actually. You can see this portion and this portion. This black is there. No, this is a rack. And we have, these are the screws. We have screwed the server. So it has a depth inside. Okay. When we pull it out, actually, like some one hand long it will be. The depth is almost, it's less than one hand, but maybe from shoulder to palm or so, wrist or so, that much depth the rack has. So this if you see here, there are blue lights, right? Vertically, there are four blue lights. So this is a rack of four 1U server. You can see here, this one is one server. This is another one. This is another one, and this is another one. So this is the thickness of a 1U server. Now, if you look at the second picture, this is a uh, wider one. This is a 2U server. So this 2U or 4U, I'm not sure, but definitely not 1U. So this is like a 70 core server, whereas the top one, 1U server is like a 16 core server. So as the capacity or how what to say, how powerful or how compute power based on the compute power, the thickness of the server will also increase. So this I think is U server, I think. Yeah, this is it. So these are two U servers. You can see here. From here to here, it is one, and from here, this is the second server. So you can see them, right? They are stacked one on top of the other. Here also you can see the servers are stacked one by one on top of the other. So this is how in the data center, in the racks, the servers are screwed and stacked. Okay. So this is just a simple example wherein we have only minimal, but in Google data center, they will have like lakhs of such high-end servers, and accordingly, the number of racks will be in thousands. Okay. Now we'll go back to, give me a minute. Now we'll go back to our session. Yeah. Mm. So these are, I think, we talked about server, and then I think in the lecture there is also some mention about the components of the data center, like there will be the cooling mechanism, the fire protection mechanism, redundant power, connectivity, monitoring system, etc., etc., will also be there. Okay. So this is this is how a data center will look like. I mean, this is about, so typically a data center will comprise of large number of racks, with number of racks arranged with, and each of the rack will have a lot of servers or mounted. Now, we have these servers in place, but how do these servers communicate with each other, right? So we need to have the networking also. Server need to communicate with each other, and also from the outside world, people should be able to connect to the services that these servers are offering, right? The applications are run on the servers, that is, they offer services. So end user should be able to connect to these servers and consume these services. So to end user should be able to connect and consume the services. So for that, we need what is known as networking. This is in general covered under data center networking. So data center networking is slightly different from the regular networking because of the major reason that all the servers, all the networking devices, middle boxes, everything is in the control of the same administrative domain, right? In normal network, I mean, different ISPs are there, and each ISP is a different administrative domain, right? So when we are connecting to the data center, for example, when I am accessing Google search, the packet from my home or my laptop will go from one ISP, it will go to another ISP, and then probably it will reach Google's DC, wherever the nearest DC from my home or from India, it will reach the nearest DC. And once it enter the DC, this entire DC network, the entire data center network with thousands or lakhs of servers and interconnected using switches and routers, is handled by Google. But this is one ISP, this could be another ISP. So normally in the traditional networking, when the packet gets routed over the core network, they pass through different networks administrated by different people. Whereas within the data center, it is a single administration, because my data center, I own it. So I will have people to design my network and take care of the network operations, connectivity, and administer the network. Okay, so in what way DCN differ is majorly in the fact that in data center network, it is a single administrative domain. Then, yeah, then we will see to it. And in general, if we look at the data set, normally whenever we draw it as, there will be internet like this. Then from the internet, there will be some core routers, which will then get into the, this will be the here the data center starts. Okay, this is internet. This is the DC. DC. This will be, there will be another switch. Switch. There will be will be again multiple layers of switches will be there. We will see to it. Okay, how it is done. And then we will have the racks here. Okay, so there will be one more. Hmm. Okay. This is just a rough diagram. So this is how in a hierarchical manner, typically the data center network grows like this, layer by layer. On the top layer, the one that connects to the internet, we call it the core routers. That will be less in number. So it has a tree shape in general. It follows a tree shape. And the root, the number of routers in the root will be lesser, and as it comes down, the number of switches and the networking device increases, because as the how much ever racks you have, you need to support, you need to have those many layer 1 switches. Then you will have even lesser number switches, and as you go up the tree, the number of device will reduce. So this is a typical layout. Actually, in this layer, there are more switches. I didn't draw it fully. Okay, so that is when you will be able to better appreciate it. So at this layer 2 were there, here 4 is there, here probably 8 or 16. So accordingly, it grows actually. And in a data center, typically there are if we see, there are two kinds of applications or workloads run in the data center. One is you like end user will be accessing some servers, and end user or a client will be accessing some service. Okay, so it comes from the internet. It goes via one of these routes and go here. It will be processed, and then it goes back. That is one kind of request. Another kind of request is like especially the data mining and MapReduce kind of application, like the Google search. Okay, so it's not handled by a single server. So when a request comes, probably when a request comes here, it will be given, it will go here. The server will see, okay, it's a search request, so I need to split it and give it to n number of other people to process it. So this gets this request get splitted up, and it will be shared across multiple servers, and all of those servers will do their part of processing, and then the final result of the query will go to the main server who took up the query, and then the response will be sent back. So there is communication between the servers also. Okay, so we call these traffic as east-west traffic in data center. Sorry, east-west traffic. Okay. So in general in data centers, these actually contribute to a large portion of traffic. East-west traffic is higher than the northwest traffic. Northwest traffic is the one that is coming from outside road. So a request will come, and then the server will spin up a lot of parallel computation requests. Then parallelly that request or the query, the search query will be processed. Then the result will be culminated here, and the response will be sent back to the user. So these kind of east-west traffic is, I think it accounts to 70 or 80, not exactly sure of the number, maybe 60 or 80% or so of the data center traffic is actually this east-west traffic. So one difference, so one characteristic for this data center network is that generally the so since they are communicating with the servers which is sitting in the, it could be this application could be sitting in the same rack. So this rack may have one guy here, one guy here, one guy here. So it could be that this portion of the request is processed by servers in the same rack, or it could be one in the neighboring rack. So the RTT, or the time it takes to reach to the destination and come back, is very less. We call that as RTT, right? Round trip time. So round trip time within the data center networks are tiny. Normally, when we access the internet, right, it will be in the range of milliseconds. So if you do a ping to Google, okay, we can see that if we do a ping to google.com, we can see how much is the time that packet is taking to travel all the way from my laptop to the Google server and come back. So I can get the RTT from the output of a ping command. So that will be normally in the range of milliseconds. Whereas for the data center networks, the round trip times are very small, in the range of microseconds. And you can see here, right, there is a lot of interconnections. There are multi-path across, like every server is reachable to every other server using multiple path. It's not a single path from a source to a destination within the data center. There are multiple paths. It's a massive multi-path topology, and majority of the time, the applications, the east-west traffic that goes across the servers, or the applications that run in the racks or in the servers, are latency critical. So it's important to ensure that the bandwidth is, the load is balanced across all the links properly, and the request reach and the response also takes and uh, comes back in the specified amount of time. So it is actually a latency or tail latency critical. And another is like for the data center, for this particular use case, right? This is a tailored use case. It's different from the normal networking or the internet routing use cases. So DCN, data center network, have the opportunity to come up with their own L2, L3, and L4 design. L3 and L4 design. Okay, I will tell an example here. If you're thinking what is this L2, L3, and L4 design, as I just mentioned about this Google search or MapReduce kind of application. So how it happens is, so for example, if you see that we have a switch here, okay. Just assume this is one port. These are the other ports. Okay. So there is another server here. Assume that this is a server. Okay. This is another server, another server. These are the ports of the switch. This is switch. This is P1, P2, P3 and P4. This is another. Okay. So from the external user, this server got the request. Now the server found that, okay, it's a Google query or it's an application which needs to be split up and processed. So what it will do is it will send, it will split the workload based on the application. It will do the splitting and send it across to this is S1, this is S2, S3 and S4. So this server, since all of them are connected via the same switch, S1 will send the request for one, two, all of them. Okay. So S2 will be doing the processing, S2 will receive it, S3 will receive and S4 will receive. Now all of them will do the processing, and what sometimes it so happens that they do the computation and they all will start sending the response. Response will be sent, response will be sent, and response will be sent. So response has to go to S1, right? So this particular port, the egress port, there will be a queue. Since a lot of packet comes at the same time to the same port, the egress queue gets built up and there some packet drop happens. Packet drop happens. This leads to, we call this scenario as incast. So it creates, so because of this, the characteristic of the application, there is a, it so happens that the the worker nodes, maybe S2, S3, or 4, we can call them as worker nodes. Worker nodes process the request and send the response almost at the same time, causing a microburst. Microburst means a burst or an inflow of packets, or a large number of packets get sent in a short period of time. So this microburst can actually cause a eat up the queue, because all of them comes from different ports. The incoming port is different, but the outgoing port for all of these packets are same. It has to go to S1. So there is possibility that this queue gets built up and packet drop happens. So this with typical TCP, it takes time to identify, because packet drop has to happen, RTO has to happen, then the withdrawal will happen, and then the congestion will come down. So for data centers, due to this problem, this have a detrimental effect on the throughput. There is something called DC TCP. That is designed data center TCP, which kind of optimizes this problem and solves this. So this is what we mean when we say we can design L2, L3. So based on the kind of applications that it's a tailor-made setup, right? So the kind of applications that are run in the data center, and the latency requirements that these applications have, based on that one can design L1, I mean L2, L3 and L4 protocols. Okay. So that is what this we mean by that. Then okay, so I just came to this topic because I took up this statement. Let's go back to our data center network. Okay. So yeah, so the we told that in what way DCN is different, because it is in the single administrative domain. The RTTs are very tiny, and the applications that run are latency critical, etc. So to design such a data center and to have the networking, it's actually challenging because of the amount of interconnections that is available, and to make sure that load is balanced and resources are managed across networks and servers. In addition to that, uh, majorly in cloud data centers, different not vendors, different tenants run their application sometimes on the same servers. It happens. So one need to ensure that the virtual machines are properly assigned, created, isolation is ensured. So there are a lot of aspects that are challenging when it comes to data center networking. Because of this complex nature, the interconnection, the isolation that one needs to provide, so complex interconnection, complex topologies. One needs to take care of load balancing, as there are, it's like equal cost multipath, right, across every rack. So these many paths are laid out, so it has to be utilized also. Load balancing has to be there. Then we need to ensure latency, it's low latency has to be ensured. Then resources have to be properly managed, and across tenants isolation have to be taken care. So all these are aspects or requirements and challenges of data center network. Okay. Yeah. Now, yeah. So where did we come from? We started with the rack. Okay. Then we moved, and yeah, we just checked. Now, let us go to data center network elements. Okay. Let's see what are the network elements in a data center. Screen is visible, right? Yes. Right. In a data center network, so I mean topology is almost similar. This will be the core router. Then we will have the switches. Okay. Then we will have what is called as the racks. Now, on top of each rack, we will have a switch, which is called as top of rack switch. Okay. This one will be like that. Okay. This will come one, two. Okay. So this top level one, which connects to the internet, is called the border router or the core router. Okay. This level of switches is called tier 1 switches. This is tier 2 switches, and the ones that are on top of the rack is called as TOR switches, TOR. That is top of rack switch. TOR, which is there is one more way, top of rack, and there is one more thing called EOR or MOR. That is, EOR is end of rack or middle of rack. So in EOR, what happens is there will be lot of we won't keep the switch. There won't be one switch per rack. Instead, there will be this array of racks, right? All these racks, all the servers that are there in all of these racks will go to. There will be a switch here. They all will go here like this. I mean, no, it won't be a single line, right? It will have n lines, or like that n line will be there. Like that it will go. So in M that will be in like EOR is end of rack. So this is the line of racks. At the end we will have a switch. If it is MOR, instead of here we will keep it in the middle. So we will have racks on both the sides of the switch. So connection will come like this. So the problem with this is the cabling. So because but we reduce the number of switches needed here, but it makes the cabling very, very difficult. A lot of cables, like from each rack, if suppose we have a 1U server, 42 cables, and like that, if we have some N servers, those many cables will go to the switch. Those many number of ports also the switch should have. So that is difficult. So because of that, normally the top of rack is what is utilized. Okay, so TOR switch is like if I have like 40 uh, 1U servers, the switch should be having 40, at least 40 ports for all the 40 1U servers to connect. So in general, we have 24 port, 32 port, 48 port switches. So based on the whatever kind of switches available, those many um, servers will be connected. Normally, 1U servers won't be kept in these large data centers because they are very, it's like a laptop or maybe only slightly better than a laptop. Uh, so in general, the data centers, these giants that the data centers, they will be like 4U or at least 2U or 4U servers. So accordingly, the TOR switch should have those many number of ports in it. Okay. This is a high level component. So another data center typical DC structure which Cisco recommended is like this again have the internet like this, and we have the core routers, CR. Then there will be aggregation routers, and AR. Then we have the switch. So this will repeat for this side. Okay. Then we will have the racks. So here, I mean, it's similar only, a hierarchical architecture, a tree-like structure. So we call this the core router, the one that connects to the internet. The AR is the access router or the aggregate router. So the one underneath, this is the L2 network. This S is switches, and all these are top of these are racks. Okay. So there is a top of rack switch over here, okay, to which it connects. So this is, I mean, in generally, this is how the structure will look like. So when packet comes, because there are multiple paths here, there will be load balancers also running in the data center. Like the middle boxes, there will be load balancers running, and they will be taking care of ensuring that the load for a particular application, the if the application have multiple instances running across multiple racks, it takes the load balancer takes care of distributing the load across each of these servers properly. So load balancer will receive the request from external interface. It receive from external interface. Then it will directs the workload within the direct the workload within the DC, within the DC. Okay. So then the results will be sent back to the client. So client will not be aware of any of these things. So as you when we all keep using consuming these applications, right? We use Amazon, we use Google, YouTube, and whatnot. Flipkart, Myntra, everything. All of these are actually running in one of their data centers, and there are load balancers which actually takes care of distributing the load, right? But we as end users are not aware of any of these things. I'm sending my request, I'm getting a response back. So all these are taken care within the data center. If load balancing is not there, then it happens that if load balancing is not there, then the number of users or the consumers of these applications are very, very, very huge. So if load balancers are not there, if multiple instances are not run, then the users will start feeling that delay. It's been, I mean, beyond a point we will sense, okay, it's going round and round. I'm not getting the response. So the user experience will go down. So, for example, we have there are competitors also, right? Bing is there, which is again my search engine from Microsoft. We have Google from Google search from Google. So if something goes wrong at the Google's data center or its application, and if I'm using it and I'm not getting the search query results faster, we'll tend to switch to another application, right? Which also provides a similar output. End of the day, I am trying to get some address or get some results or something that I'm searching for, right? End of the day, I need the result for it. It doesn't matter who gives me the result when we have two people doing the same thing. So it's very important for these providers to ensure that user requests are processed in time and the responses sent back within the given time frame to ensure best user experience. So load balancing is very actually critical for these right. Mm. And the other concepts. Yeah, next. Okay. Now we'll look at what are the design objectives of data center networking. What are the objectives when we are trying to design a network layout? This is how the switches and routers should be connected. I mean, why should we design it in so and so manner? We are doing it because we want to achieve certain objectives, right? So we have our objectives per set, and based on the objectives, the data center, the networking will be designed. So it is very important. This objective aspect is very important because until we have a clear-cut objective of what we want to achieve, we cannot design how we are going to achieve it. So the major the common DCN or data center networking objectives across TCs would be, let me save this. Yeah, so we were looking at data center network objectives. So the first and major objective is uniform high capacity. This is a one important objective. Uniform high capacity. So irrespective of high capacity should be there, like one should be able to transfer the data within the DC at a very fast rate. That's what when we talk in terms of capacity in networking world, that's what we mean. And between any two servers, no matter which rack it is, okay, high capacity links between two servers, no matter where they are located. Matter irrespective of their location. Of their location. Like we have one rack here, one rack here, nearby. So I have this server. Okay, we have them communicating. So this capacity, and I have another server little far away. And we have another this guy, and there is another server here, and these people are communicating. Irrespective of where the application is, where the server is, which rack it is, all of them should have uniform high capacity. That is one objective. And another one is performance isolation. So it's not that in DC we run a lot of applications, right? It's not like one single application, of course, for Facebook and maybe Google search. That is for one big app. That one example DC we have seen, right? But in general, in the data center, there are thousands of applications that are run, and majority of the times, multiple applications run on the same servers. So there has to be performance isolation. So traffic of one service should not affect the traffic of another service. For example, if we take, I'm not sure if this would be just a hypothetical example, just think like this, where we have two, in this rack, we have two servers, okay? So this is the top of rack switch. So anything that has to come to this has to come via this Tor switch, okay? So maybe I have Gmeet here and I have Google Docs here. So if there are people will be using Gmeet and Google Docs. So traffic destined for Gmeet should not eat away the switch or the link capacity, and the Google Doc application that is running in another server should not get affected. So or maybe if we have both of them in a one we have two application, app 1 and app 2. The and this is the Tor switch, and packet is coming for both of them. The packets or the traffic destined for app 1 should not interfere and affect the service of app 2. That is what we mean by performance isolation. And then ease of management. Ease of management is very, very, very important when we are dealing with such uh, large scale data centers, right? A single mistake will lead to blackout, and you would have remember in between, like Facebook was not reachable for I think a couple of minutes or hours or so. So those kind of issues will happen if it is not easy to manage. Once a network goes wrong, it's very hard to fix it up. It's very, very at this large scale, it's very hard. So ease of management is very, very important. One should be able to, like, when we are scaling it up, like tomorrow I want to add a new rack, I want to add a new server, or I want to add like 10 extra racks. We already have these many racks in place, and accordingly we have the topology, but I'm going to add another set of maybe 10-15 racks and servers. So one should be able to add this without much of a difficulty, which would be able to add these racks, the servers in the rack. Accordingly, the necessary switch also should be added. It should be easy to do that, and it should be easy to manage all these things. So, and moreover, when the applications in as you know, like in the data center, it's not that all the applications run on the bare metal. Lot majority of them, or a lot of them run on virtual machine. So VM migration is something very, very common that DC guys do. For example, I have a rack here, I have three racks here, okay? Assume that these guys are almost full, so I have couple of applications running here. Maybe one tenant withdrew here, one tenant withdrew here, and I have some space, free space available. They will always try to move the applications that are running in this rack to these two, so that they can power it down. If there are no applications running in the rack, right, accordingly power saving and all those can be done. That server itself can be powered down if there is no application. So they always try to migrate for the applications load across VMs, across servers, racks, to ensure optimum power utilization, optimum load utilization. Complex algorithms runs, and they take the decisions accordingly. So when all these things are being done, it should be easy to do all that. When you migrate it from one place to another, the IP address management should be easier. It should not, the connectivity should not be disturbed. So this is also an important goal, ease of management. So in general, to achieve this, flat addressing is what is used in the DC, in the L2 side. So here we saw that. So okay, in the previous, I think, right up, we had the core here in the L3, and we had the L2, right, where there were switches and so in general, flat addressing is something that is used so that servers can have these movement, and the management becomes easy. One can easily do a plug and play. Then Yeah, so now let's take a look at one of the common data center network topology, which is called as fat tree topology. So in fat tree topology, it's similar, kind of similar only, like tree structure. Okay, this is the typical how it looks like. So we have the in the top, we have the core, then we will have the aggregation switches, and the aggregation switches, this is how they get connected. And then we have the top of racks. Okay, we will have the racks here, and we call this this unit as pod. Okay, so this is pod 0, pod 1, pod 2, and pod 3. Okay, so this is the aggregation, this is the core, this is the aggregation, this is the edge switches. Okay, so this is the typical. Okay, sorry, yes, this. Mm, sorry. Okay. This is connected. This is connected to this guy. Here it's okay. This is connected to this too. He's connected here. Mm, this too. So this is the typical connection in a fat tree topology. Here, this ensures in fat tree topology, they ensure that the uniform bisection bandwidth is ensured across all the links actually. So this uniform high capacity is something that is ensured in fat tree topology. So to ensure that, why this term fat tree means, because as you go up, for example, if this is a 1 Gbps link, this is a 1 Gbps link, Then as we go up, so the total, if we sum it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So, so the total aggregate bandwidth is 16 Gbps, right? So as we grow up, the upper switch needs to have maybe 1 Gbps or more. And as you reach the core router, the bandwidth it has to support increases. So that's the reason it's called as fat tree. Okay. So typically, as you come here, this will be fat. Then, I mean, this link will be, the bandwidth of this link will be higher, but then it becomes little thinner, 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 little thinner, thinner, thinner. And as it goes down, it becomes thinner, thinner, thinner. So that's the reason the terminology factory came in. Okay, that's to ensure that the bisection bandwidth is uniform across all the links. So if that has to be ensured, it means that this particular when we cut it across, this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But when we cut it here, this here also, this 16 Gbps has to be ensured. So if that has to be taken care, then the bandwidth that the core support should be higher than the underlying 1 Gbps. Another topology is the leaf spine topology. The difficulty with this topology is that even if one needs to, yeah. So this is the rack and this is the Tor switch. Okay. Yeah. So even if I need to communicate with a neighboring rack, one need to uh, go up all the way here and then come back. Okay, so this is like couple of n number of racks are this is not I mean I drew it as rack, but these are like servers. Okay, so they could be in a single rack. So if from one rack to another also, if they need to communicate, the number of hops needed is 1, 2, and then only it can reach the neighboring rack. So this is one disadvantage that factory topology had, and that's the reason another topology called the leaf spine topology came up. Just have some basic idea, I think that should be good, because these are little complex concepts. So in leaf spine topology, how it works is we will have core, then we will have a spine. These switches are called spine. And then the leaf. Leaf is the one. So everyone is connected. Okay. Sorry. So here now, if I need to go from like from one rack to another rack, it's um, immediately from here you go, you get here. So there is one hope is actually being saved in the leaf spine topology, but it also have the disadvantage that as each of the as this leaves increases, spine also should increase, right? As we have one more thing. This all the spine switches should be able to connect. Now, the switches will can always get limited by the number of ports, right? So those difficulties comes into picture with leaf spine topology. I think you got some fair idea of how they typically just have some imaginary picture how the structure is like a tree structure. That should be good. Maybe we can go back to our problems now. Quickly go through the previous year's question. Okay, right. It's visible, right? The screen. Screen is visible, no? Yeah. Okay. So, yeah, you can actually type in the answer. Which of the following is not a typical component of a data center network? Servers, network, storage, workstation. Which of them is not part of a data center network? Can you type in the answer or you can unmute and speak as well? Yeah, that's a very easy question, right? Yeah, workstations are not part of the data center network. So the answer is D here. Right. Okay. What is the total number of servers supported by 4-port switches in leaf spine topology? So there is this formula, right? If there are k switches, it support k power 3 k cube by 4 servers, right? Right? If there are k board switches, how many servers does it support? It is k cube k power 3 by 4. So it is 4 into 4 into 4 by 4, which is 4 star 4 star 4 by 4. So what is the answer? So it is 16. Okay, so the answer to this question is 16. So if we have a 4-port switch in the leaf spine architecture, it can support like 16 servers. Okay. Which of the following statements is or are correct about modular data centers? So modular data center is nothing but The container data centers, right? High mobility, which of the following is true, correct about modular data center? It is high mobility, higher operational cost, lower operational cost, and faster deployment. So which of these are correct? So we have seen, right, in container data centers, within a container, the entire DC is set up. So it's very easy to carry it from one place to another. So it's highly mobile. So it's mobility aspect. And one another aspect of container DC was lower operational cost, right? It's actually smaller. It's set up within a container. The cooling, all those is minimal power consumption. The number of servers that we keep is also smaller. As the scale is smaller, the operational cost is also small. And it is faster deployment as well. So you don't need to actually build a building and have the AC cooling mechanism in place or anything, right? Those infrastructure costs are not there because it is within a container. So that is why lower operational cost and faster deployment. We can quickly set it up and deploy it. So the answer is A, C, and D. Right. Which of the following statements is or are correct about top of rack in data center networking? A data center design where all servers are connected to a single switch. Mhm. Core is or are correct is what the question is. If you know the answer, please type in. I'll check it out. The other option is core switches are typically used as a Tor switch in a data center. Third is a network architecture where switches are placed at the top of the server rack. A networking technology for wireless communication in data centers. Which one is correct here? It is a network architecture. So a data center design where all servers are connected to a single switch. No, that is not even possible, right? So that's not Tor. That's not top of the rack. It's a design where all the servers in a rack is connected to it and the switch is placed on top of the rack. So it is option C here. Okay. A network architecture where switches are placed on top of the rack, top of the server rack, and the servers are connected to it. So the answer here is C. Put anyone type in the answer. Let me see the chat. Yeah. So the next one. What is the purpose of the spine switch in a factory topology? Spine switch in factory. Let's cross check the question. Just give me a minute. Let me cross check. I think that term is wrong. It should be, it can't be spine switch because in factory we don't have this term, right? Spine switch. So I assume it should be the edge switch. Yeah, I think it is edge switch. So let's assume it to be edge switch. If that is the case, to connect the servers to the network, to provide redundancy for the core switches, to provide high-speed interconnection between pods, and to aggregate traffic from the edge switches. So maybe we can skip this question as this doesn't seems to be right to me. Because if we assume it as an edge, then we cannot assume it. So I'll skip this question, okay? Right. Which of the following transport layer protocol is specifically designed to address the TCP incast problem? This I think you can answer, right? We saw what TCP incast problem is and who solves that. Can somebody type in the answer? Which of the following transport layer protocol? It is DC TCP, data center TCP, which is designed to solve the incast problem. I hope you understood what TCP incast problem is. Right, the answer here is what is the primary purpose of a data center fabric? To place switches at the top of a server rack to provide a high-speed backbone network that interconnects switches and servers, to manage power and cooling within the data center, and to provide storage for data center applications. So the answer here is to provide a high-speed backbone network that interconnect switches and servers. We call it the data center fabric. Okay. So the answer here is B. Basically to interconnect the switches and servers and have high-speed connectivity. Which of the following statement is bar are incorrect about end of row in data center networking? So can you go through and type in the answer? End of row design, remember, right? Instead of keeping the switch on top of the rack, we will keep it at the end. If there is a lane of racks, to the end we will keep the switch. At the end we will keep the switch. So option A is end of rack design helps decrease the number of switching devices. The question is which one is incorrect, okay? Require smaller cables from servers to switches compared to Tor, lower rack space and cooling power than Tor. For servers in the same rack, layer 2 traffic efficiency in EOR is lower than Tor. So EOR design helps decrease the number of switching devices. Is it correct or wrong? So this is correct because we are having only one switch for the complete set of racks. So it helps reduce the number of switching devices. Then the second one is require smaller cables from servers to switch as compared to Tor. This is actually wrong because at the end you will have the switch placed. So the one, if we are considering like from left to right, we are moving and the switch is placed towards the, for example, do we try to- right, if we have one rack like rack like this, and if we have the switch here, then the first rack, the length of the cables required will be very high, right? We have rack, then switch, right? So the length of the cabling will be high, and that's a one major disadvantage because of which cabling becomes complex. EOR is not used. So the answer here is B. Right, answer. So the other thing also we can see lower rack space and cooling power than Tor. Lower the rack space. Yeah, that's true. Because we are not placing a 111 switch on top, right? The heating needed for the switch comes down. That space can be utilized by a server. Right. For servers in the same rack, where true traffic efficiency in EOR is lower than Tor. Yeah, that's because um, the propagation delay would increase actually. Otherwise, it's just go to the Tor and come back. Now it has to travel all the way from the to the end and then come back. So the distance the packet has to travel is higher. Maybe I'll show it off after I'm done. I'll share the other screen and maybe show it off. Okay, that's all. We are done with the questions. All right, maybe I will just quickly show this also once and then we can wind up presenting. Again, present your share screen. Next. Next. So, what is meant is when we have it like this, in the top of the rack, we have the switch, right? So, if there is a communication between this application and this application 2 and 1. So packet has to go here and then come back here. How much would be the distance? Hardly how many meters, right? Maybe can't estimate how many meters it would be. Very few, right? But if it is a end of the rack, it will be like this rack is here, this rack is here, this rack is here, this rack is here, this rack is here. Like this, it will go, and you have the switch here, right? So if this application packet app 1, app 2, this has to travel all the way here, and then it has to come back. This is definitely longer than the distance that it has to travel. All the other things remains the same, but it is this that increases. So efficacy probably will come down. Right, all right. Any other questions? If not, I'm done. We can then close the session. Yeah, I mean, I think if no more doubts, then I'll close the session. Thank you all. Thank you for attending the session. Hope I was able to help you out in some ways with the concepts. See you all next week, same time. Thank you. Bye bye.